Hi, welcome back. We've just been working on understanding how to take a partial derivative and what it means. Um, once we decide that we're comfortable taking one derivative, let's take another derivative. So, for example, we could take f of xy and take the partial with respect to x, and then take the partial with respect to x again. Um, when you do that, one way you can write that is like this, where we say partial, so del squared divided by del x squared of f of xy, or del squared f del x squared, or del squared z del x squared. That would be a partial with respect to x twice. You might also write f sub xx of xy. Now, you might also decide to mix your partial derivatives. So you might see something that looks like f of xy. So what does that mean? Well, that's f sub x sub y, which is saying first you take the derivative with respect to x of f, and of that you take the partial with respect to y of that. And so this is something to be aware of, that when you take f sub xy, that's really taking a partial with respect to x first and then y. So it's kind of backwards in that way. So we'll do some calculating of these partials. But before we do that, let's first talk about something that there's actually a course here at Queens College about, which is partial differential equations. So you talked about differential equations in single variable calculus, and if you're dealing with functions of multiple variables and you have an equation that involves partial derivatives of an unknown function, that's called a partial differential equation. And often you're looking for solutions to these equations. A solution is a function that satisfies the equation. So let me give you two classic examples that, especially if you're taking physics, then you'll see, and maybe you've already seen. The first one here is, here's a function defined on points x, y in a plane. And what we could do is we could look at uxx plus uyy is equal to 0. Right? This is saying take the derivative with respect to x twice, and take the partial with respect to y twice, add those up together and get it equal to 0. That's an example of a partial differential equation. Solutions to this equation are, you often use that if you're trying to figure out something about heat on a surface or how fluids and electricity flow through a surface. Another example, another classic example, is the wave equation. Okay, and so another way to write this is utt is equal to a times uxx. So in this example, our two variables correspond to a position and a time, so something's changing over time. And so you can talk about describing the positions of waves as a function of time, which is useful when you're talking about water waves, when you're talking about sound waves, when you're talking about light waves. Yeah, I'm drawing the same thing each time, same thing. But this wave equation allows you to find solutions for these physical concepts. All right, so these are examples of partial differential equations. Now let's take some partials. All right, so here's an example. X cubed plus x squared y cubed minus 2y squared. Let's find all second order partial derivatives of this. So to do that, first we take the first derivatives of this. So derivatives with respect to x, 3x squared. Y is a constant, so we get 2xy cubed. And the derivative of a constant is 0. Then the derivative with respect to y, we get 0 plus, now x squared is a constant, 3x squared y squared, and the derivative of this is negative 4y. So those are the first order partial derivatives. Now the second order, we take f sub x, and now we take the derivative with respect to x, and the derivative with respect to y. So with respect to x, we get 6x plus, now x is the variable, y cubed is the constant, so 2y cubed. And now if we take the derivative with respect to y, then x is a constant this time, so we get 0, and x is a constant, we get 6xy squared. So now we do f sub y, and we want to take the derivative of that with respect to x. So with respect to x, then y is a constant, so we get 6xy squared, and the derivative with respect to y is 6x squared y minus 4. All right, so what do we notice here? Well, one thing that we notice here is that 6xy squared appears twice. And so what we've noticed is that f sub xy seems to be equal to f sub yx in this example. All right, and that's not a coincidence. In fact, Clairaut has a theorem from, this is way back in the mid-1700s, where suppose that you have a function that's defined on a disk that contains a and b. If both f of xy and f of yx are continuous on D, so if both of these mixed partials are continuous, then f of xy of AB is the same of f of yx of AB. So work a little bit to understand this supposition. So the only time we can apply Clairaut's theorem is if we if we take the x derivative, the y derivative, sorry, if we take the x derivative and then the y derivative, and then we take of the function and it's continuous. And then if we take the y derivative and then the x derivative, and that's continuous, that's the only time we can apply this theorem, and we have that it didn't matter which order in which you took it. So when we're in these nice cases, like a polynomial, a bunch of polynomials, or a bunch of functions that are just continuous all the way down, then you can just order derivatives however you want. You could take x and then y and then z and then z, or you could take z and then x and then y and then z. You can just take your partial derivatives however you want. That makes your life as easy as possible. All right, let's stop there. The next thing up is the chain rule.